Welcome to this video comparing the gravitational and the electrostatic forces. Now in this unit on electrostatics, we're going to do this several times, compare the gravitational and the electrostatic analogs of a few different things, namely force, field, potential, and potential energy. And we'll get to the other ones later, but since we just talked about Coulomb's law, we're going to do some important comparisons. All right. So let's start off by addressing an important point that's very obvious but is also very overlooked, and that is that objects have mass, but they can also have charge, okay, at the same time. Now because they have both at the same time, that means that they can be experiencing a gravitational force due to the masses interacting, and an electrostatic force due to the charges interacting. And we just figured out that Coulomb's law describes that interaction between the two charged objects. The gravitational force describes the interaction between the two masses. Now we know this as m times g, right? And another expression, another way to write that is big G times m1 times m2 over r squared. So you can see the similarities here. Now some contrast between the two is that this force is only attractive. So it always attracts two masses to one another separated by some distance. This one over here can of course be attractive or repulsive. And that's something we have to keep in mind based on the signs of the two charges. Now in this example here, what we're going to look at is drawing a force diagram and then figuring out the net force that would act on a charged ball. Okay. Now, when we are looking at the gravitational force, we are comparing the attraction, or we're describing the attraction between the ball and the earth. Okay, I have a platform here that I'm going to explain in a minute, but in this case we're looking between the ball and the earth. Now this would obviously be the ball's mass. You could also make it m2, and then this would be the earth's mass. Now at the same time, I'm going to go ahead and give these each a charge. I'm going to give this platform here a positive charge, and I'll give the ball a positive charge. Now the mass of the platform is very, very small compared to the mass of the earth. Okay, so let me go ahead and put that information here. The mass of the platform is much, much smaller than the mass of the earth. Okay, so when I'm thinking about the gravitational attraction between these two things, I'm really only using this platform to help create an electrostatic force. I'm not really considering the fact that there's a gravitational force between these two things. So in other words, if I added the gravitational force between these two things, it wouldn't really be any different than the ball and the earth. Okay, so instead of having to write two different gravitational forces between the ball and the earth and the platform and the ball, I'm just going to do one. So I'm going to go ahead and draw a force diagram down here. This is for the ball, okay? And since these are both positive, the ball is going to get pushed upward. So I'll go ahead and draw that in, and I'm going to label it electrostatic force. Now, the gravitational force, of course, pulls straight down. I'm going to label that mg. You could label it fg if you want to as well. But now we need to figure out what is the relative magnitude between the two. And if we go up to these two equations here, the answer is going to lie in this constant. Okay. And the constant, Coulomb's constant, as we just described recently, is 9 times 10 to the 9th Newton meters squared per Coulomb squared. That's 9 billion. Okay, keep that in mind. That's a really large value. On this side, over here, the universal gravitational constant, big G, is equal to 6.67 times 10 to the negative 11th Newton meter squared per kilogram squared. So you can see how similar they are. This is for coulombs for charge, this is for kilograms. So this is almost the prefix of pico. That's like times 10 to the negative 12th. I mean, this thing is tiny, 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 tiny. On this side, this is huge, right? It's more than mega. And so what we can say then is that the electrostatic force is much, much stronger than the gravitational force. Even if we're talking about these massive, huge masses, these two numbers, compared to the tiny little values that we usually have for charge, because you're multiplying all of this by a really, really high number, okay, 9 billion, and you're multiplying this by a really, really tiny number, you can see that the electrostatic force is many magnitudes stronger than the gravitational force, okay, if we were doing a one-to-one comparison. Now, a cool thing that you can do, however, is you can actually levitate objects, and we're going to look at a scenario where this happened, where they actually figured out the charge of an electron, and this is Milliken's oil drop experiment. You may or may not have heard of that before, and we're going to get into it in more detail later because we need to learn a little bit more. But basically what you can do is you can get mg to be the same as Fe. Okay, there's a way to do that, and you can think of it as you're going to have to change this over here more than you're going to have to adjust this, right? And once we get this stabilized and these are balanced, we can actually figure out what the charge is on the thing that's floating in the middle.